Hey everybody, welcome back. So, last time we had a rather lengthy discussion about the existence and uniqueness theorem for first order equations, both linear and nonlinear alike. And that had most decidedly a very pure math topic. What I'd like to do now is kind of bring ourselves back to reality a little bit and give some more context behind why we're studying differential equations. So, let me go ahead and start by telling you that there's another class of differential equations that we would like to study. So in general, we have a rate function that is given as a function of both t and y. But what would happen instead if we got rid of the dependence on t? Right, and we've seen examples like this. Remember our free fall example? So free fall, we had dv dt equals, what was it? Let me think. It was, force of gravity. So it's constant 1 minus v, basically. It was a pair of constants. So it'd be constant minus constant times b. This would be an example of one of these kinds of differential equations where we don't have, like, our derivative doesn't depend on time. So we can actually say that we would like to study those kind of equations where derivatives are time independent. Okay, and these equations have a name. These are called autonomous differential equations. Okay, right. Autonomous because they are effectively self-motivating or self-actuating. And if we went back up and included time dependence, then this is a non-autonomous differential equation. But for this video, and I believe the one coming up, there's the next. We're splitting this section into 2 videos. We're going to be looking at autonomous equations and showing that these do show up in more than just physics examples. In fact, we're going to make this section about population dynamics. Right, so we're going to bring some context back here. So remember at the beginning of our series that I gave an example of this equation as an example of a first order linear differential equation. It is also separable, but that's beside the point. This guy is autonomous, right? So it doesn't depend on time in its derivative. Yes, y is a function of t, but the derivative itself can be written strictly as some function of y itself. And that's what makes this autonomous. Now, why would we care about studying this kind of differential equation? Well, remember, if I give some context here, let's say that y of t was given to be the population size of some, it's the number of individuals in some population at time t, and t we're going to take to be greater than 0, just because this is an applied problem, and we don't study experiments before we start studying them. So that means that time can usually be taken to be greater than or equal to 0, because t equals 0 is when we start studying the problem. But notice that y here, if this is measuring a population size, y2 must be greater than or equal to 0. I can't have negative population size. I mean, mathematically I can account for it, but physically it's a nonsensical solution. So if y is indeed the size of a population, then dy dt is measuring how quickly that population grows over time. And what this equation says, is that the rate at which my population grows is proportional to how many individuals are in that population at that time. And we can state this a little more cleanly if we interpret this a little bit differently. R, by the way, I haven't said so. R is, it could be, for population dynamics, R is usually going to be greater than 0, and this is constant. Right? It's usually some parameter in the system. But the point is that I'm going to look not at dy dt, but I'm going to look at dy dt relative to the population size. And what this differential equation tells me is that this rate of change relative to the number of individuals in that population at that time is always constant, right? And this growth here, this ratio is called the per capita growth rate. And if anybody speaks Italian, you can tell me that this means per head, so per capita growth rate. And this law that we're imposing says what happen, or asks what happens when this growth rate, when this per capita growth rate is a constant. Well, we know how to solve this, and specifically, if we say that y at 0 is some size, some y naught, then we can go ahead and solve this guy very, very quickly. It's separable, and we wind up with y of t equals y0 e to the r times t, and we need to include the fact that we are not looking at any solutions where t is less than 0. So, or any part of the domain where t is before we start, where t is less than 0 before we start looking at this population. But anyway, that means that constant per capita growth, so constant per capita growth is exactly equal to exponential growth. Not too shabby there. So there is a simple solution to a physical law where we're saying, great, if we know that our population is growing with a constant rate relative to its size, then we know that this population has to be growing exponentially. Wonderful. And this actually does work out for mostly for unicellular organisms. So think e.g. bacteria, right? So bacteria are asexual reproducers, which means they just they don't need partners to reproduce. They can split via mitosis, and bacteria will double in a very quick amount of time, very rapid growth rate here. But the point is that since every individual is going to reproduce at this same rate, that means that the total rate at which something is going to grow, or where the population is going to grow, the net growth, is proportional to how many bacteria are supplying that growth rate, which means that these guys are following exactly this Malthusian growth model, right? Malthusian, named after Malthus. There we go. This is the Malthusian model for growth. Great, so bacteria follow this. Many unicellular organisms also do this as well, and in small quantities, diploid organisms also follow this paradigm, right? When they're very, very small and they're not really competing against each other, they're just worried about reproducing because they don't have much energy to go and do anything beyond eating, sleeping, and making little babies. Okay, that's about all there is to that model. So the question now is what happens if we penalize large population sizes, if per capita growth is penalized at high populations. Sizes, there we go. And we know this is true. We know this is something that's exhibited in nature, right? For many, think like weeds in your garden, right? Eventually, they look like they're growing out of control, but eventually, there's only going to be a certain number of weeds in that garden, right? They're going to bud out just about anything else that tries to grow there. And if you try to put anything else in there, say you wanted to put a flower amongst your weeds, your flower is going to be budded out. That's competition. So in other words, your little garden patch there can only support so many organisms. It can only support so many plants, which means that for low populations, for low population size, for low, and I'll just say low size, just to cut down on the writing. For low size, our rule should be that we want to increase the population. And for whatever too large might be, We're going to decrease the population. We're going to get rid of that flower that you tried to plant. How dare you try to put something pretty in your garden when there's weeds present? So this can be modeled very, very easily with the idea that your per capita growth, dy dt per y, should be capped at a certain size. And we're going to say this is 1 minus, no, do I want that? Yeah, we're going to say that this is proportional to 1 minus y over k. And these constants, let me explain. R is the same as before. R greater than 0 is the growth parameter. Right, it's the same guy from before. And k, on the other hand, notice what happens with k. This term, this thing in the parentheses, is what's dictating whether or not this population grows or dies. If y is less than k, then that means that 1 minus y over k is greater than 0, which means dy dt is greater than 0. So this is growth, right? So that checks off our first box here. But our second rule, notice what happens if y is greater than k. Then 1 minus y over k is now less than 0. And that means that dy dt is less than 0. And we have death, right? So we shrink the population. And that checks off our second criterion here. So this model here, right, this is a proposed mechanism by which we can satisfy those two parameters, those two rules. And this K is called the carrying capacity. Right, it's a measure of how many resources your population, or how many individuals your resources can sustain, can sustain. And this model here, let me go ahead and kill off that arrow, it's bugging me. Right, this box, this is the logistic growth model. And this is what the vast majority of organisms on this planet satisfy. And this goes for viruses as well. So those of us living in 2020 right now, you are very, very familiar with this model for a viral epidemic. So here's the deal. There are many, many ways that we can try to solve this guy. And in fact, dy dt, if we go ahead and put this in the standard form for the logistic equation, this is how we usually see it. And we can go ahead and try to solve this guy. I'll do it very quickly here. 1 minus y over k is r dt. It's a separable equation. The guy on the right is no problems. Very, very easy to solve for the family of antiderivatives of a constant. On the left, however, we do need to... this is a partial fraction, so we got to separate this denominator. And I believe what we actually wind up with here is something very simple like this. We'll make sure that's still a square bracket. There we go. And that's over k, not over 1. Okay, I believe that is correct. Yep, okay. If I integrate this guy, I wind up with natural log absolute y minus 1 over k. No, I don't get the 1 over k because that's pulled into a u substitution, 1 minus y over k. And that's still equal to RT plus C. I can simplify this a tiny bit more. Are you following me, cameraman? Yep, there we go. If I exponentiate and drop the absolute value sign with the acknowledgement that pluses and minuses get absorbed into a new constant, this is not the same C as the one up above, that is a different C. And I continue C e to the RT, so multiplying both sides by or clearing the denominator. Yeah, so y times c e to the RT. I bring all the y's over to one side of the equation, so plus y times c e to the RT equals c e to the RT. And finally, I factor out the y and divide by what is left over. Wonderful, great, spectacular, stupendous. That's awesome. This is a solution for logistic growth. Now, Does anybody know what that looks like just off the top of their head? I sure as hell didn't when I first saw this. So what I'd like to do here is kind of show you that this particular dude, this particular solution, or it's a general solution, I suppose, has a particular form. And if I were to plot this, I would see that there are actually constant solutions to this equation. Oh, come on, there we go. I could use c equals 0, and that would give me a 0 solution. And I could use k, and k should give me another solution. I do need to make sure that I'm using an initial condition here, y of 0 equals y0. And I will wind up with a k floating around in here somewhere. Oh, did I not do that? I did not do. I absorbed that into a constant, so that's over a k. So this should be a c over k. That makes more sense. A c over a k. K should show up in this equation. And what winds up happening here, you will see, is that your solutions tend to increase exponentially and then flatten out toward the carrying capacity, and they are exponentially decreasing above the carrying capacity, and then they are increasing exponentially in between 0 and k. And all of these curves, these are called sigmoid curves. Sigmoid because they look like sigmas. They look like Greek S's. Or they look like S's, not like Greek S's, but yeah. So the point is that we're using Greek to explain a Roman letter or Roman character phenomenon, which is kind of weird. But anyway, this is a sigmoid curve, and this is indicative of logistic growth. This is a logistic dynamic. These are logistic dynamics that we see. And that's really all there is to it. That, yeah, sure, this was a pain in the ass to have to compute, right? You had to pull out partial fractions. You had to solve and do a whole bunch of algebraic gymnastics just to get down to a general solution. Now you have to go and figure out a particular solution. That is just too much hassle. So what I'd like to do for you is show you in the next video how we can go ahead and solve this equation. I'll say solve with quotes, right? We can solve this differential equation, this logistic growth model, without actually solving for an explicit solution.